To start this session.
In progress.
I did. Okay, good morning and welcome to this morning session of the workshop. In this session, we will have two local CAUST professors, both recognized world leaders in the fields they're going to talk about, present. And first up, we have Professor Daniele Boffi, who is the leader of the research group in numerical methods for PDEs here at CAUST. He's going to talk about reduced order modeling of parametric PDE eigenvalue problems.
Okay, I think my mic is working, right? Yes. Okay, thank you very much for the introduction. Thank you very much for the invitation. It's a real pleasure to be here in this event. Well, I feel a little bit embarrassed because I don't have anything stochastic yet in my talk, even though, I mean, I'm talking about a project that eventually should maybe reach the point where I'm going to talk about some stochastic PDEs. So for the moment, we are still in the deterministic world, and well, you'll see what I'm talking about. And first, I'd like to acknowledge my collaborators. So basically, we have two groups. There was a pointer here, yes. There were two groups that I'm collaborating with. Well, it doesn't work anyway. So one is with Florian Bertrand from Chemnitz, and the other one with Francesca Bonizzoni, who's now moved to Milano, Mox in Italy. And then two of my former postdocs, Abdul and Gopal, now they went back to India, and one of my actual PhD students, Mutats. I was working on that. So that, as I said, there are two different projects that somehow I have some intersection. There is some merge between the two, as something separate, but I will give reference to what I'm supposed to do. Okay, so probably I have to click on the page to make it work, right? Yes. Okay, so this is the outline of my talk. Let's start with some very brief introduction about reduced order modeling. I think you know what I'm talking about because I'm planning to use reduced order modeling for eigenvalue approximations. Okay, so this is a field that has not been explored so much in the literature. So there are some papers, but I mean, as I will try to show you, there are a lot of differences between reduced order models for standard PDEs and for eigenvalue problem arising from PDEs. A lot of time will be also spent on motivating examples because I think it is good to have some feeling of how things can go on. Okay, so what is the classical setting for elliptic PDEs, right? So you have a parametric space M. For the moment, as I said, is deterministic, so d-dimensional. I have a Hilbert space V and Berliner form A and the right-hand side F, so that in the setting of Lax-Milgram lemma, I mean, I'm just looking for a solution U that solves AUV equal FV for all V in V, okay? And this U depends on the parameter mu because both Berliner forms and right-hand side F may depend on this parameter nu. And what is the idea behind the reduced order model? Well, the idea is that when you want to solve the so-called high fidelity solution with finite element space, for instance, because I'm a finite element guy, so you choose this finite element space VH that has a dimension NH that in general can be very large. And then you try to solve the discrete problem AUHV equal FV for all V in VH. This is a matrix problem, of course, a linear system. And then your solution UH is what is called high fidelity solution, which in general is very expensive to compute. And would like to have some ideas how to reduce the complexity of the resolution of this problem. Okay, and in this setting, UH is considered as the reference solution. So we're going to compare the solution of the reduced problem with the high fidelity solution that is computed by the finite element like this. And the reduced space, let's call it a VROM, reduced order method, or reduced order model, as you prefer, is a space that has a dimension much smaller than NH, but then the dimension of VH, right? And the idea is that you want to solve this reduced problem. And what is the desired property of the solution of the reduced order model? Well, the desired property is that this is a good approximation of the high fidelity solution. So in practice, what we do, I mean, we try to balance between the complexity of the solution and the accuracy of the solution that you find. Okay, so you are available in this case to trade a little bit the accuracy in terms of the complexity of the solution. So this is what is very well understood in the framework of standard PDEs. And in our project, we talk about eigenvalue problem. So how do we formalize the numerical approximation of an eigenvalue problem arising from an elliptic PDE? So in general, you consider this Hilbert triplet. Let's say that H is L2 and V is a subset of H1, just to fix ideas, if you're interested in something that is similar to the Laplacian. And V is compact in H. Okay, so this is just H1 compact in L2. Then you have a symmetric uniform elliptic bilinear form A. This could be the same bilinear form that we had also for the source problem that we shown before. And B now is the right side, is another bilinear form, depending on the parameter mu. And what we assume in our presentation today is that B is uniformly equivalent to the scalar product of H. So you might think of the scalar product in L2 if you want, right? Maybe with some parameter mu, but uniformly equivalent to the scalar product in L2. Then the eigenvalue problem has the following form. So you solve AUV equal lambda BUV up to the parameter mu. Okay, in the case of the Laplacian, for instance, A is the usual grad U grad V bilinear form, B is the scalar product in L2, and then you may have some dependence on mu on both matrices on the left and the right hand side. Okay, and what is well known for the theory is that since all matrices are symmetric, since you have the compactness of V in H and the ellipticity of A, well, the ellipticity could also be relaxed, but it's not restricted to consider it elliptic. Then we have all the eigenvalues are real, first of all. I'm living in a real world here, so I'm not taking complex eigenvalues, but our project aims also at dealing with complex eigenvalues in the future, but for the moment, everything is symmetric. Then they're positive because of the ellipticity, and because of the compactness, all the eigenspaces are finite dimensional, and the eigenvalues are a sequence diverges to plus infinity. Okay? So this is the standard theory of compact operators. Right? And we normalize the eigenfunction by using the bilinear form B. Say they have L2 norm equal to 1. Okay? And it's also well known that from the characterization of spectral operators, we have that the space V can be seen as the span, I mean, as generated by all the eigenfunction of this operator. Okay? And now the same thing, well, there is one thing that I'm hiding here. That's why I put this slide here. So how do we number things? So this is what usually people do if there is no parameter. Lambda 1, lambda 2, lambda 3, U1, U2, U3, right? But if there is a parameter mu, even in the very easy situation where the parameter is real, just one dimensional, like here. So here we have mu, the parameter on the x-axis, and you have the value of the lambda on the y-axis. Okay? So you see that in a very simple situation like this one here, I will show the equation later on. So the eigenvalues represent curves in the space, and these curves may cross. So it's clear here what is the first eigenvalue. I would say is this magenta line, right? It is on the bottom. But what is the second one? Is it the brown, or is it yes, it is the brown in this number here. But is this really what we want? Well, I mean, if you look at the other picture, maybe this is a better way of sorting the eigenvalues. The colors are different, just not to make confusion between one picture and the other. But on the right-hand side, it's clear that the first one is the one in blue on the bottom. Right? Then you have another eigenvalue, which is brownish, then another one, which is purple, and so on, right? And you see that the brown and the purple, they cross. So which one is the second one? Which one is the third one? Well, depends on the value of the parameter. Okay, so even numbering the eigenvalues may be a problem in the case of parametric eigenvalue problems, and this is the main difference between the source problem and the eigenvalue problem. So in the source problem, you have one right-hand side f, and you are looking for one solution u. Then, of course, you have parameter mu, so the solution depends on the parameter, but there is only one solution depending on the parameter. For eigenvalue problems, you have many eigenvalues, infinite many, and when you want to approximate numerically this, you just take a finite number of them, not infinite many. And the question is, how do the the discrete eigenvalue correspond to the continuous one. And even the numbering, as I said, is not so easy to detect. Okay? But for the moment, let's forget about that. Let's go on formally with the derivation of the problem, and then we'll see with the numerical examples what it means. Okay, so the high fidelity solution for eigenvalue problem is constructed exactly the same as for the PDE. So you take the finite element space VH of dimension NH, and then you solve a generally high expensive matrix eigenvalue problem, the generalized eigenvalue problem, right? AU HV equal lambda HB UHV. Okay, so this is a generalized eigenvalue problem with a matrix on the left-hand side originated from A and a matrix on the right-hand side originated from B. Okay? And again, I mean, here it's very easy. The compactness is for free because of the finite dimensionality of the problem. We have a finite number of discrete modes, lambda 1, lambda 2, lambda NH, right? That, I mean, they are exactly NH if you count them according to the multiplicity. Okay? The problem is symmetric, so there is no problem with algebraic and geometric multiplicity, is the same. And you also here normalize the eigenfunction in such a way that the bilinear form B applied to UH is equal to 1. And again, it's well known that the discrete space VH is just generated by all the discrete eigenvectors. Okay? Okay, so this is the high fidelity solution, so the one that we want to approximate by the reduced order model. And the reduced order model consists, same as before, of finding a space VROM of a dimension much smaller than NH, and to solve this reduced model eigenvalue problem, which with a smaller matrix. So just to give ideas, I mean, the matrix of the previous problem, the high fidelity could be 1,000,000 degrees of freedom. Okay, the matrix here could be 3 by 3, 5 by 5. So it's a huge difference in terms of complexity. But of course, now the question is whether we have an efficient method. I mean, again, we are trading accuracy with complexity, and we would like that the reduced solution is a good approximation of the high fidelity solution. Okay? And our project, as I said, aims at designing efficient reduced order schemes for the approximation of this problem, with the property that the discretization is robust, efficient, and that it works also for multidimensional problems. So when D is large, and eventually our dream would be also to deal, maybe in collaboration also with the group of Raoul, to reach the point when we get some stochastic eigenvalue problem. Okay? And when we started this project, we looked at the reference, and basically there were two main references, not so many. The problem was not so studied so much. And there were two main references. This is one of the two. And Fumagalli, Manzoni, Parolini, Verani in 2016. So they deal with the first mode well separated from the rest. So in the picture that I showed before, there was one eigenvalue that was isolated, the number 1. And this was clear, it was number 1, because for all values of the parameters was the lowest. And this was separated from the rest. And in that case, they basically produce what people knew about the reduced order model for PDEs. Okay? And well, this is easy because basically you're reducing the problem to only one solution among the many that you have, the infinite many that you have, right? So it's not so difficult to generalize what you know for the source problem to eigenvalue problem if you consider only one eigenvalue that is separated from the others, in particular if you consider the lowest one. Then about the same time, I think they were working independently about at the same time, and then just by coincidence, the second one appeared the year after, is a paper by Holger, Volmuth, Dikov, who dealt with now the simultaneous approximation of a number of eigenvalues, not only one. They considered the first k modes, so 1, 2, 3 up to k, and they claim that if you approximate all of them at once, then you get good results. So they claim, they proved, they showed all the theory about that, right? And if you can read the comment that was in that paper, so basically they said, well, if you have one single eigenvalue, k equal 1, then we are in the case of the previous paper. But if k is larger than 1, you take the first 3 eigenvalues. If they're separated from the rest of the spectrum, then you can just work with them, and then you're okay. Okay, so this was the state of the art when we started working on that. And then we started, first of all, try to understand those results by computing some examples. Okay, and very, very easy, because I mean, maybe you know my idea. My idea is that if there is something you don't know, I mean, there is always something easier that you don't know. So it's better to start with the easiest configuration and try to understand how it works. Otherwise, it's difficult then to do theory and to understand mathematically what's going on. Okay, and so we started with this motivating example, which is very, very easy. Parameter one-dimensional, mu is one-dimensional, is a perturbation of the Laplacian. So you have a diffusion matrix A, which is a diagonal, as 1 in position 1, 1, and as 1 plus mu in position 2, 2. So if mu is equal to 0, is exactly the Laplacian. If mu is different from 0, then you have some perturbation of the Laplacian. And this is exactly the problem that gives rise to the plot of the curves for the eigenvalues that I showed before. Because, of course, here is very easy to compute the exact solution by hand, by separation of variables. So the eigenfunctions are constant in mu. They don't depend upon mu. They're just the standard eigenfunction of the Laplacian. And the dependence on mu shows up in the eigenvalue lambda. You see, usually for the Laplacian, you have m squared plus n squared up to a factor, depending on the size of the square, if the domain is a square. And here the mu shows up as a multiplicating factor of n squared. So you have 1 plus mu multiplied by n squared. So if mu is equal to 0, again, you get the Laplacian. If mu is different from 0, you get a perturbation of the eigenvalues. And now, if you plot, this is the way we computed the picture on the left-hand side, the one that was on the right-hand side before, right? So on the left-hand side, you have exactly the picture of the curves described by the lambda in this formula here. Okay? And on the other hand, on the right-hand side, you have the color code coming from your computation. So if you try to compute the solution for different values of mu, and if you number them according to the local numbering coming from mu, then you get the color code from the right. And clearly, I mean, the curves are the same, right and left, but the colors are different. Okay? So what is the consequence when you do reduced order model? Okay, let's try. So we try to reproduce exactly what people do for instance, for the POD approximation of the problem, proper orthogonal decomposition. I think you all know how it works, right? So we take a number of sampling in my parametric space. In this case, I partition my interval in subintervals of length 0.1, ranging from minus 0.9 to 0.9. So I don't go wider in my interval because I want the matrix to remain positive definite. So mu cannot be smaller than minus 1. Okay? And then the POD basis is constructed. How is it constructed? So here we deal with the first eigenvalue. So we are in the framework of the first of the two papers that I showed before. So we form the snapshot matrix just by considering as column vector all the eigenvectors corresponding to the first mode for the different sampling. Okay? So I have, I don't know, 20, 19, I don't know how many samples. Then I have 19 columns that correspond to the first eigenvalue computed for different values of the parameter. Okay? In this case, it's very easy because the eigenvalues, the eigenfunction, they don't depend on the parameter. So this means that all the columns are the same, just multiple from each other. Because when I move the parameter, the eigenspace is the same. So I just get another representative of the same eigenspace. Okay? And the idea of POD is to compute the SVD, the composition of the snapshot matrix, to determine the most important modes in my snapshot matrix. So try to reduce the dimension of the space by neglecting those vectors corresponding to the smallest singular values. This is the idea of the POD. Okay? And in this case, theoretically, what we think is that since the matrix S is formed of columns that are multiple from each other, the rank of S is equal to 1. So I'm expecting the singular value decomposition of S to give one non-zero singular value, and all the others should be 0, theoretically in exact arithmetics. So I'm expecting to have a reduced order space of dimension 1. And if I do my homework, well, when Abdul came up with these numbers, I said, "Are you sure did it correct?" I made it recompute things, but this is what happened. These are the singular values of the matrices for different size of the mesh. And well, the scale on the y-axis is in logarithmic scale. So you see that there is a jump. I mean, there is one singular value that is separated from the others, and the distance is much wider than you think because of the logarithmic scale. So I mean, if the first singular value is of range of 10 or 100, the second one is of the range of 10 to the minus 2 in the first picture. So there is a gap, but it's not so sharp as I would imagine. So I would have imagined one singular value different from 0 and the other all 0, because this is what happens in exact arithmetics. But of course, this is the real world. So you compute an eigenvalue problem, you are solving. So by solving, you commit some error. Then you form your snapshot matrix. You compute the SVD. Also, the SVD has some arithmetic precision. So you don't have exactly 1, 0, 0, 0, but you get one singular value that is separated from the others. And then the idea would be to consider a reduced order space formed by the singular vectors that are more dominant in this the composition. Could be only one, could be two, could be three, I don't know how many. So how do you do that? I mean, the standard high fidelity problem, as I said before, is a generalized eigenvalue problem with two matrices A and B corresponding to my bilinear forms. And the reduced problem, this is the typical thing that you do for the POD, is just the projection of the continuous problem onto the discrete space. So once you form the reduced matrix V, right? Is the collection of the first significant singular vectors coming from the previous decomposition. Then A ROM, reduced order, is V transpose AV, and B ROM is V transpose BV, so that the reduced problem is just the generalized eigenvalue problem corresponding to A ROM and V ROM and B ROM. Okay, so you solve this problem, and now you want to test how it works when you apply it to a value of the parameter that was not in the snapshot matrix. Okay, so let's test it on points like minus 0.75, so something that has a non-zero second decimal place, so that is not included in the sampling. And if you take the ROM dimension equal to 1, the one that theoretically should be the good one, you can compare now the high fidelity, the column in the middle, with the reduced problem, column to the right. And you see that there's a good agreement. I mean, they are a good approximation, so they're not perfect. But as I said, we are trading accuracy with complexity. And here, please notice, we are solving a one-by-one problem. So the computation of the eigenvalue is just a division, nothing else. Okay? And the accuracy is good. What happens if we increase the dimension of the POD space? Let's take equal to 2. Since, I mean, even the second singular vector is not exactly 0, so let's try to take also the singular, the second singular vector. You see that if I move from the previous one to the next one, there is some difference in the fourth decimal place of the computed thing. And in the picture on the top here of this slide, you see the value of the eigenvalues when the POD dimension increases for 3 different choices of the high fidelity mesh. So you see that 1, 2, 3, up to the third singular vector, you gain something, and then you stabilize to the value of the high fidelity solution. I mean, this seems to be working. I mean, this is what you usually get when you do a POD reduced order model for source problem. And this is the same also for the eigenvalue, but we know we have the theory here, because in that paper it was shown that if the first singular mode is separated from the others, everything should work, and this is a confirmation of that. Okay, let's now try to do something a little bit more tricky. Let's try to compute now things for the third eigenvalue. The third eigenvalue is which one is the third one first? I would look at the picture to the right, and for us now the third is the blue one. So the one that at each point of the parametric space corresponds to number 3. Right? And you can see that you have 2 corners in this curve. Okay, so if you look at that curve there, you see 2 corners, sorry. So there are 3 branches. So one steep, then one almost flat, and another one that goes up. Okay, so basically now if you think of the snapshot matrix formed by using the third eigenvector for different values of the parameter, and since each curve has a constant eigenvector, so this means that now the snapshot matrix would contain 3 different kinds of eigenvector, basically. The one corresponding to the 3 branches of these blue curves that has 3 pieces, right? Okay, so let's try to repeat this procedure and see if it works. So we have the singular values. Well, since now the rank of the snapshot matrix is 3, theoretically, we have 3 singular values that are separated from the others. Again, it's not precise in terms of machine precision, because there is some discretization error, but we have three single variables that are very well separated from the others. And now if I try to use a reduced order dimension equal to 3, this is what I get. Okay, so on the middle, you have the high fidelity solution, and to the right, you have the reduced order solution. Well, they match pretty well. So now you might wonder, so what's the problem? So because I presented the thing in such a way that I try to induce you to think that is wrong, right? But we get good results. Okay, so we get good results, but there is a but. Everything looks good, but if you look at, but I'm hiding something. So the column obtained to the right, the one with the reduced order model, is one of the eigenvalues that you compute with your 3x3 reduced order system. And when you do a 3x3, you have 3 eigenvalues. So which one did I pick up to compare? I picked up the second one, which is something that I know because I know the exact solution. But if I didn't know the exact solution, it was impossible for me to predict which one I should take. I mean, I would imagine that if you reduce the system, you should take the first one, because you are working on the eigenvectors that are relevant for your problem, so they should be the first one. Or since we are approximating the third one, you take the third one. But here we don't take the first one, we don't take the third one, we take the second one. Why? Well, if you look at the picture here, if you look at this picture here, this is just a zoom of the thing. We are approximating this blue here, right? And this blue, as I said, is made of 3 components: this part, the middle, and then the other one here. And so at each point of the parameter, the eigenvalue that I'm considering is the one in the middle among the 3 that I'm considering. So here, for instance, at the beginning, this branch of the curve is between this one here and the other one there. The blue is made of 3 parts, right? And one part is this, one part is that one that goes up, and the other one is this one that goes here. So at each point, the blue is always in the middle between the 3. So that's the reason why the second reduced eigenvalue corresponds to the one of the high fidelity solution. But this is something that I know because I know the exact solution. Otherwise, this method is impossible to use. I mean, it's not a method that works. So it's clear that by using a very naive POD approximation of the eigenvalues, you don't get a method that can be of any use. Okay, and okay, so let's now try to use the simultaneous approach, which is the one that was suggested by the paper by Volmuth and her collaborators. Okay, so now the simultaneous approach would mean that you have a blue curve, and now you take all the eigenvalues that are somehow related to that, and then you have 4 of them, because in addition to the previous one, you consider also the other one that creates this cluster among the blue curve. Okay, so let's now try to get all of them at once. Okay, now you have a POD of dimension 4. Okay, now it works. So now you get that the third discrete eigenvalue, the one with the reduced model, corresponds to the third of the high fidelity, because we are considering also the first model. I mean, all the 4 simultaneous approximations. So this is a confirmation of the results by Volmuth. Well, there was no need to confirm the results, but I mean, you see that this is the correct approach. So this means that you have to be a little bit careful with these things. And what is the essential message about these motivating examples that I'm showing you? And then I will go quickly to our solution. Well, the essential message is that in case of isolated eigenvalue, it should work well because it's separated from the others, right? But in presence of crossing, then we should deal with all the involved eigensolutions simultaneously and not just separate the blue one from the others. So this is the message that I had at the beginning. And also, let me mention also the paper by Schwab and Andre's PhD students, because this is very important, because it's the first point where you see that the eigensolution corresponding to parametric space may be non-smooth, like we have in this case here. Yes, Raul. Yes, now I will show you more example to tell you that the essential message that's written here is wrong.
Okay.
Because this is what I deduced.
Even with a buffer, it will not help.
The problem is that you really have to start from the first one. This is the problem. So if you have a cluster, say that you have 1, 2, 3 isolated from the others, and then you have a cluster in the middle, separated from the other that are higher, you cannot work only on that cluster of separated eigenvalues. You really have to include also the lowest one, which is actually what was written in the paper by Volmuth, but was not emphasized. So in the paper by Volmuth, they said, let's for simplicity consider 1, 2, 3 K. If you work on that, then it works. But then my stupid intuition was, suppose that I have 3 plus 1, 3 plus 2, 3 plus 3, 3 plus K that are separated from 1, 2, and separated from the others. Then it should work also if you're in the middle of the spectrum. No, in the middle it doesn't work. You really have to start from the beginning. And these are the other numerical examples that I'm showing you now. Okay, so with a more sophisticated example, very simple again, but more sophisticated. In the middle, I mean like this. So this is the solution of this problem that now we're going to describe. Look at the blue and the green curves. The blue and the green are a cluster of 2 eigenvalues that are separated from the one that come before and that come after. If you do a simultaneous approximation of the blue and the green, you may come up that we converge to the lowest one. Yes, but here, I mean, you see, if you only look at these two, the crossing occurs only when everything generates. But the problem is that in this curve, blue curve, for instance, you have now the eigenfunction depends on the parameter. And the fact that you are now forming your snapshot matrix by considering all variable eigenvectors introduces more variability in your eigenspace. And when you compute the eigenvalue problem, you know very well that you are minimizing a Rayleigh quotient. Right? And the more things you put in your space, the lower you go with your eigenvalue. So that's the problem. So even if you are considering all the snapshots that correspond to things that should stay on the curve, which is blue or green there, then when you combine things together, when you form the POD basis, then you introduce some randomness, that something fictitious. I mean, that is not, that leads you to the lower eigenvalue. So this is what happens. And this is critical. I mean, we were not expecting that, but of course, a posteriori is very easy to see that this should happen. So this is the equation, just very quickly, because otherwise I'm running out of time. But I mean, now we have a problem with the parameter of the diagonal. The diffusivity is 1 mu, mu2 now. And we don't have the exact solution, but we compute the exact solution, which is like this. And this is what happens. Now let's suppose that we form the snapshot matrix only by using U3. Okay? At the beginning, everything seems to be okay. But if we now, let's go on this. Isolated U2, even U2. U2 is the one that is here, right? So this brownish magenta curve is completely isolated from the rest. Okay? So you start from there, and the continuous, the solid lines are the one that correspond to the high fidelity, and the dots are the one computed by the POD for a test value of the parameter. Okay, and you see that when you increase the dimension of the reduced space, you still converge to the second one, which is good. This is what you're expecting, because these dots are superimposed to the high fidelity solution. This is what you want to see, right? But let's consider now more snapshots. So you add more entropy, if you want, to the system, because you put more things, and then you more perturbation in your numerical data. When you increase your ROM dimension, you see that even if you are forming your snapshot matrix by considering high fidelity values on this curve, then when you increase the POD, you go down and you approximate the wrong eigenvalue, you go down, even if the second eigenvalue was separated from the rest. So this is what surprised us. So really, there is really something different in the eigenvalue problem than in the source problem. Yes, please. You should play volleyball, not basketball. I know.
We know that power iteration method is working well when largest
The same.
eigenvalue is
I think
separated.
it's similar.
So why here not? Why we cannot compute with power iteration largest one subtracted from matrix, reduce dimension by 1, then again apply power iteration method to the rest and successively compute?
I think you should shift also, not only power iteration, because you know that also with power iteration, even if you start from the first vector, which is orthogonal to the first one, then by the perturbation introduced by machine precision, you will always converge to the maximum. So this is what I mean, it happens, right? So and this is a similar phenomenon also here, the one that also that we had for the SVD. So you might think of starting with, so theoretically in exact arithmetics, if you start power method with a vector which is orthogonal to the first eigenvalue, then you converge to the second one. But numerically, when you implement it, you have the error introduced by the truncation error, by all these things, and then you always introduce components that are also along the direction of the eigenvector you were orthogonal at the beginning.
Okay,
So,
second question. I was
yes.
thinking about Lanchos method. It's also connected to question of Raul. It's good to compute K largest eigenvalues, but we compute not K, but 2K eigenvalues. And from this 2K, K are accurate and the rest is not so accurate. Can you comment this? Is it somehow relevant to this or not at all? Or?
This I don't know, and we never tried. I mean, what we use here, we use just MATLAB computation for the eigenvalues. So we use AIX, which is based on Arnoldi. But I'm afraid that really what you need here to know is to be able to get some insight on how the crossing are. So if you are blind, if you don't know anything about the structure of the solution, so this is my message out of this example. If you don't have an idea of the structure of the solution, it's difficult with a POD to get the right one. So this is my impression. And well, I think that I probably skip all the other examples that I had. I had several examples, but since you were interested, and this is a good thing, you made me slow down, and this was good also. So I have several examples. I can be very happy to discuss with you as much as you want. But what is the moral of this example for me? So the moral is what I was telling you right now. I mean, the moral is that there is no moral unless we can try to identify some structure of the hypersurfaces defined by the eigenvalues. So hypersurfaces in more than 1D, right? So you have this led to one of our side projects that is to design a greedy algorithm in order to track the crossing of the eigensolution. So try to see if we find a way to really be able to label the eigenvalues in such a way that the color code of the discrete solution is the same as the one of the continuous one. And this is what actually we did. And let me see, since I want to show you also something of the last part, I will maybe describe the code afterwards, but I want to see how it is in action now. Let me tell you what I want to do. So this is an example of one exact solution for one particular problem. So we have one parameter only here. Actually, it's a 2D problem, but we froze one of the two parameters. Mu2 is equal to 0.7 and mu1 is equal to ranges in one interval. Okay? And we look only at the dependence on one parameter. And this is the exact solution. Okay? And on the next page, you see the result of our algorithm. So these are discrete computations. You see that only for certain values of the parameter. And we have chosen the value of the parameter in an adaptive way, in such a way that we're able to reproduce the behavior of the continuous solution. So if I go back and forth now, you can see that the discrete one are perfectly superimposed to the one of the continuous one. So for instance, there is a crossing clearly between between here, right? So here there is a crossing between the magenta and the brown here. Okay, so if you look at the discrete one, you can recognize that we have here this order of the magenta and the brown, here the cross, and then the swap. Okay, so we were able in our code to deduce this crossing. How do we do that? So this is the way it works. So we start with a very coarse mesh of the parameter space, like this, 3 points only. We solve the eigenvalue problem in a window. For instance, here we decided to solve between 0 and 250. We want to search for all the eigenvalues in that window, which means that for the 3 values of the parameter, we may have different number of eigenvalues. Because, for instance, on the left, we have only 4. On the right, we have many, more than 10, right? Because this is what happens. In that range, we have that number of intervals. And we have some a priori strategy. And the a priori is something that we adapted an idea of Nobile and Pradovera for doing that. So the a priori dictates a color matching between this point and this point, for instance. They are all blue. So this, for the a priori part of my code, belong to the same band. Then there is this black here, black, and black, and so on, okay? And then, of course, here there are many colors that don't correspond to anything because here you have more eigenvalues than on the others. So some of them disappear. There is also some unassignment cost in the a priori phase. Okay? And then there are some dashed line here. That means that my a posteriori, so after the a priori phase, where I put the colors in the dot, then I have some a posteriori procedure that certifies the interval to see whether it is fine enough or not. And in this case, it's not. Why? Because the a posteriori says that this black here, well, should correspond to the black correctly, or should also correspond to this sign here. So the posteriori says, I'm not sure that the a priori did a good job. Could be something wrong, right? And also here, this eigenvalue could correspond to the correct one, which is here on the bottom, but will also correspond to this on the other one. Okay, so this means I'm not certain that I did a good job, so I have to refine. And this happens in both intervals of my grid. So I perform a refinement. Again, after the refinement, I perform some a priori. So here I have the blue, here I have the black, and so on. And then I perform the a posteriori. So now the posteriori is better than before. So there are much less dashed line in my picture. It means that, for instance, the correspondence between the blue, all the blue, it is certified. So the posteriori said, yes, it did a good job. This is a one band.
I'm sorry, when you say refinement, you mean spatial or parametric?
Parametric.
Parametric.
So here the x-axis is the parameter.
Okay, and second question, just I forgot actually. Here it's just one parameter, but you think about multi-parametric problem, yes?
Yes.
So you just for simplicity explain us case with one parameter, yes?
Then I will show you also 2D
Okay.
case. I mean, the idea is that also in 2D, we always resort of comparing 2 points. So we perform the a priori and the posteriori along the interval that connects the 2 points, even if we are in 6D. Right? And so we have a greedy mesh that allows us to identify always pairs of points in such a way that we can work on one interval. Right? And in this case, as I said, I mean, the posteriori is happy now with this interval of the parameter because all the matching are certified by the posteriori. In the second interval, there is still some uncertainty about this one here. And in the third one, there is uncertainty here, while the fourth one is okay. So we should refine the 2 intervals in the middle. Okay, let's do it. We refine the 2 intervals in the middle. And finally, now the only critical point remains this one here for the posteriori. So we refine that one here. And finally, the posteriori is happy. So it certifies that this crossing procedure is okay. So we were able to manage all the procedure. And since you're interested in multidimensional, and we also are, let me go back once to the continuous solution, because it's not a coincidence that the posteriori had to work more close to that point. It was here, was this situation here, because this is also what my eyes showed me. So when Mutas came with these results, I said, are you sure that this is the exact solution? Because usually when you have a situation like this, you are expecting a crossing, right? So I was expecting that this black line were continuing like that. And the same way, the black curve here would continue over there. Right? So this is what my intuition was telling me. And then I asked Mutas to refine much more the space mesh in order to get a better solution of that crossing, but then there was no crossing. And why was not the crossing? Because as I said before, this is a section in 1D of a 2-dimensional parametric problem. So now if we move along the other direction, then we'll get the crossing. And this is what shows you also how complicated is the situation. So this is what happens in 2D. But suppose now you're dealing with a 6-dimensional problem, because now we are doing that. We are solving a problem in elasticity that depends on 6 parameters. And there, the number of configurations that we have in terms of intersection and so on is very, very complicated. So and we are only dealing with symmetric problems, so real eigenvalues, compact problems, and so on. So suppose now that what we want to do is something more general, non-symmetric with complex values, or even when you have some stochasticity in your PDE. So this is the dream that we have, but it's a long-term project before we have to understand these things here. And
I'm sorry, very naive, too stupid question. I have operator.
There is no stupid question in
Yeah,
the business.
I have operator which depends on x and parameter. Why not to find some tensor separation of these variables and find eigenvalues for x and eigenvalues for matrix which is responsible for parameters, and then you simply find all possible combination? And
I've never thought about that, but I wouldn't know how to find eigenvalues depending on the parameters. So I'm not sure that you can get a dependence on the.
so we have matrix A which depends on, let's say, Laplace, and another which matrix B which is responsible for parametric, and you have two matrices.
Well, more than a matrix, it becomes a tensor, right? And then you have
you have tensor product of these two matrices,
well,
or two tensors.
If the structure is not, it depends on the structure of the parametric dependence. I mean, on the it's not always possible that you can separate this.
Yes,
right?
not always. Very.
No, it's not so obvious. Yeah.
But if it's possible, then it's possible. Yes, then
probably yes, but it's very simple situations. And 2D, just before trying to get to some conclusion, I mean, 2D, these I cannot show the same picture because they're difficult to visualize, but I show you just the mesh of the parametric space. So here we have the same problem as before, but now with both parameters varying. And this is the grid in the parametric space, mu1, mu2. So the 9 black dots are the dots of the coarsest mesh that we consider. Then we add some forward point in order to have a greedy algorithm, and they're the red one, and these are the ones that are kept by the posteriori. So we add all the forward point, we check the a priori and the posteriori. If the posteriori is happy with that, we remove them because we don't need them. But we keep the forward point only where it is needed. So they're on the right part of the picture. Then we go on the next level and we add more points. You see here on the left, everything is good. Then we add more. So all the reds are the ones that are added at each level of iteration until we have only one, and then everything is black. So here is the situation where the posteriori refinement said, okay, I'm okay. I don't need to refine anymore. And you recognize, I mean, as I said before, that all the checks are performed along intervals. So the grid is constructed in such a way that I can always identify two neighboring points so that I can work one-dimensionally on this matching. And well, the picture doesn't say so much, but these are the bands in 2D, and the dots are the one that we computed. I mean, if you play with the real picture that you can rotate it, you see that there is a perfect matching, and we can identify all the intersection. And we also have a data-driven approach, which was the one I wanted to say, but I will only show one result, and then I will conclude. Otherwise, my time is too little. I mean, the same example that I showed before. Now, with this data-driven approach, we are able to construct something like this. It's data-driven, so there is no physical informed nothing. I mean, it's just data. So we don't know anything about the PDE. So what we do, we create some sampling, and then for each sampling, we have n+1 data. The n data that come from the vector plus 1 that comes from the eigenvalue. And then we compute a regression between all this data to extrapolate or interpolate how the behavior is out of the sampling points. So, and this is the reconstruction that we get. So here in this picture, you have on the top, you have the eigenvalue. I don't know if you can see, there are some dots here. So the dots are where we are training our system. And then the magenta curve is the regression that we have. We use GP regression, Gaussian process regression, right? And there is also, as usual with this regression, a prediction interval that tells me how accurate I've been with this. And this, I think, is a completely different approach from the previous one, and is very promising. Now we are trying to analyze also theoretically this, and try to see what is the best regression in order to get the accurate result. So here we have a band that has a corner, and you see that by using the training data and by using this regression, we have a very accurate representation of the band for all the values of the parameter with a very good prediction interval. And here is the reconstructed eigenfunction corresponding to this. And you see that also the jump of the eigenfunction is very well captured. So we have on the left-hand side, the eigenfunction corresponding to this branch of the solution. And on the right-hand side here, these two, we have the eigenfunction corresponding to the other branch of the solution. So we jump from one eigenspace to the other automatically without knowing anything of the PDE. And this actually is something that looks very promising. And what we're working now in this direction is to try to identify the best kernel for the regression, because there are some kernels that work better in presence of smooth solution, other kernels that work better in presence of singularities. And here we have at the same time to approximate singularities because they are corners, but also smooth parts because away from the intersection, we have smooth solutions. So we are trying to do also some comparison between regression, interpolation, splines, and other ways of approximating the data in order to get good results. And this in particular works well also, and this was the motivation, was also when there is no affine dependence on the parameter, because as you know, I mean, when the POD is effective and is able to reduce the computational cost, in particular, if you have some affine dependency on the parameters like this, otherwise you have to recompute things too many times. And on the other hand, the data-driven approach works also for nonlinear problem, and we applied that also for nonlinear problems. And well, I think that I should stop here. How do I go at the end? Okay, just to draw my conclusion. Okay, just to leave the conclusion written there. And thank you for your attention.
Okay, thank you very much, Professor Boffi, for this very interesting talk. We had several questions, but we have time for a few more before we turn over to the next speaker.
Grazie, Daniele. A very nice talk. So, question: when you refer to these crossings, right? In all these approaches, one has to take into account, like you said, the loss of regularity when eigenvalues cross, right? I mean, for example, the two cross, you have this square root behavior with respect to parameters. So when you do this sort of either a posteriori or some kind of regression or interpolation, taking this into account, a priori one knows that essentially you have a finite number of crossings, right? And at each of these crossings, you have this loss of regularity. So my question has two sides. I mean, one is like, doing these approaches, can you try to extract some idea what will be the complexity, the cost, because of the fact that you have this type of loss of regularity at the crosses, and somehow you are trying to approximate a square root by this procedure? Maybe that could guide you on what is some kind of cost on the previous approaches. But the second thing is like, okay, if I know that a function has square root behavior at a finitely many points, and I do not know where are these points, right? Can I use this a priori information to actually inform my sort of regression in some way that it will reduce the cost? For example, I mean, you could think of a compressive sensing or something like that, where you try to put some basis functions that are kind of redundant, but that may have the ability to capture some of these crossings, right? So, and then eventually at the end, you activate only a very few, but you still retain some ability to approximate this thing instead of adding points. I don't know. I mean, I have these two sides of the same question somehow that.
Yes, I mean,
already.
I can follow you more on the second one than the first one, because the first one I never thought. But the second one, actually, this is what we probably would want to do. I mean, because we have this algorithm that is able to detect the crossing. And then we have this regression that works also if we don't know anything about the crossing. And I think that it would be a good idea to try to make them talk to each other. I mean, so from the first algorithm, you can get some information on the structure of the solution, and then to have some data driven that is not only driven by data, but also by some elaboration of the data.
Some a priori
The-
knowledge on what is
Exactly. Exactly. This is exactly what we want to do now. I think this is
Oh, this is what the extended finite, generalized finite elements one
Yeah.
does, right?
yes, until that, yes, the
Oh, that's why I make.
cut fem or all these things. Yeah.
Okay, cool.
Yes.
Thank you.
And of course, talking also about the regularity, the singularity of this eigenfunction in presence of crossing is what makes very hard to me to see how to do with stochastic problem. Because I mean, if you want to do some polynomial chaos, for instance, things, I mean, all the assumption that the dependence is smooth with respect to the data, right? And I think we should change the paradigm if you want to do so. Exactly. Exactly.
One question. It's not work. Yeah, it is.
It is.
How is what is the access you have to the data? You have the actual solution. What
I mean, in my examples, I'm computing the data because
Yeah, I
it's
understand
just
But what do you
an
see?
offline phase that I am available to pay. I mean, I pay an expensive solution of a PDE problem, and then I compute my data. So
But
the
and then you
only
have an uniform grid. You have
Uh,
access to the uniform or randomly sampled.
the grid, I mean, of the parameter, I mean, or the space, because I mean, what we do,
See,
we have
I
this.
understand what you see from the actual solution.
Yes, what I can do, I mean, once I fix the value of mu of my parameter, I mean, I can compute as accurate as I wish my solution by refining the space grid. And this is just a matter of waiting. This is an offline phase. I mean, I can really have a very accurate solution.
Thank you.
Welcome.
Yes, one more question.
Hi, there was a very nice talk. My question is regarding the error that you have on the reduced order model. If you can compare errors for different parameters, thinking on the optimization perspective, say I have two values of parameters mu1 and mu2, and I have some objective function that depends on the solution of the PDE. How reliably can I decide between two values of parameters based on the error that I have on the approximation?
We haven't tried to do that so far. So what we do now, I mean, we choose the dimension of the POD basis by looking at the decay of the. This is a standard thing that you can do, right?
But
so
that would be different, I guess, for different parameters.
yes,
right?
that's true.
So,
But we
okay.
didn't try to do that. Yeah.
yeah, thank you.
Thank you.
Okay, let's thank Professor Boffi again for his nice talk.